Okay, welcome back to Real Analysis. We're going to continue our work in Chapter 5, talking about continuous functions. In this fifth section, section 5.5, we're going to be talking about properties continuous functions have, namely algebraic properties. And the video lecture won't contain a lot of proofs, actually, because we've already written the proofs. A little bit earlier, a couple of sections ago, when we were looking at algebraic properties of limits, well, continuous functions at non-isolated points anyway are defined in terms of limits. And so any properties that hold for limits of functions are going to hold for continuous functions. So that's basically in a nutshell what the whole lecture is about here. Let's be a little bit more precise. Let's start off by recalling what we mean by a function on a subset A being continuous. Like I just said, if the input x0 that we're looking at is an isolated point, then just kind of by default f is continuous there. Or if you want to use the epsilon delta neighborhood definition of continuity, if you're an isolated point, there's some delta neighborhood in which x0 is the only point. So the continuity kind of happens automatically. If not, if you have an accumulation point of the domain, then we define the limit in terms of, the continuity in terms of this limit. So remember, there's kind of three pieces of information you can take from that limit. One is that the function, that x0 must be in the domain of the function because I'm taking f of x0 of it. We've said it's an accumulation point, so that taking the limit is defined, and that limit not only exists, but it equals the function value. Okay, so that's kind of our threefold criteria of what it means for a function to have a limit at an accumulation point, and the function is continuous if that limit is equal to the function value, right? And we've already talked about this. If we just say that that's continuity at a point, if I just say that f is continuous on the set A, well, I mean it's continuous at every point in A. All right, so continuity on a set just means continuity at every point in that set. I'm going to take kind of well, this is sort of a summary of what I was talking about at the opening of the lecture. That algebraic properties of limits, those things were earlier developed in this chapter. The results are results 5.15 through 5.18. There are things about constant multiples of limits, sums of limits, differences of limits, products, quotients of limits, quotients provided the denominator is not zero, of course. Those algebraic properties say that convergence is preserved under all of them. Yeah. If you take some function that has a limit at some point and you multiply it, say, by some number, that's the constant multiple rule, that constant multiple has a limit. If you take two functions, both of which have a limit at a point, their product has a limit at that point, and so on. All right. So we proved those things earlier in chapter 5. The results are 5.15 through 5.18. If you want to stop the video and look them up in your book, I would actually just go glance at those things. Well, again, at accumulation points, continuous functions, you can still see it at the top of the screen. Continuity is defined in terms of a limit existing. So those same exact facts, 515 through 518, are going to give us corresponding facts about continuity at a point. Okay, so namely, if we roll all of that together, leave that paragraph visible, that's what this theorem 5.40 says. That if you take two continuous functions, so they're called f and g, they're both continuous at some point x naught. And again, if x naught is an isolated point for both functions, then the continuity is just kind of automatic. So the spirit of this theorem is when it's an accumulation point, but it works out in all cases. So if you have two functions continuous at x naught, then any constant multiple of one of them, the sum of them, which by the way, you can get the difference as well by taking the constant multiple to be minus 1 on g, the product of them, they're continuous at x naught, even the quotient. As long as g of x naught isn't 0, then the quotient f over g is continuous at x naught. All right, so continuous functions are closed in kind of algebraic language under all of those arithmetic operations, constant multiples, sum, difference, product, quotient, quotient always having a caveat. The denominator is not 0. I'm going to take just 1 second. Some of you guys have taken an algebra course, either abstract algebra, linear algebra. Some of you are taking one now. Some of you are going to take one in the future. Depending on where you are in the math major and what the sequence is that you're taking our upper division courses. But I just want to make kind of a comment that sort of links our subject here with some of those algebraic ideas that developed in, abstract algebra here at Humboldt is Math 343, linear algebra, upper division linear algebra is Math 344. So this is just sort of I don't know, a couple of minutes of commenting, linking these subjects, trying to get you excited about this. These different branches of mathematics are not kind of isolated subjects in which you never refer to anyone, kind of on the or any other one rather. On the contrary, they're very much interconnected. These ideas that you learn in any one of these given courses in algebra, analysis, geometry, differential equations, so on. There's sort of all kinds of pathways and connections to all of the other subjects. So we're just going to kind of talk about that for just a second here. So let me denote, I'm kind of, this is somewhat standard notation, but I'm just going to kind of make it up here by C of AR. So what is A here? I could quantify it. A is just any old subset of the real numbers. Let's denote by C of AR the set of continuous functions on A. Okay, so I've written it out in set builder notation here that C of AR consists of those functions F, whose domain is A, its codomain is the real numbers, and they're continuous on A. So just to remind you that means they're continuous at x0 for every x0 in A. All right. So I'm going to use some language here from these algebra classes without defining it, but it's somewhat reasonable. I think you know what I mean by it. Among other things, that theorem we just talked about, the algebraic properties of continuity, theorem 5.40, it says that addition and multiplication, which I'm just denoting by plus and dot here for this brief conversation, those things are binary operations on this set of functions, continuous functions on A. So what do I mean by that? If you take two continuous functions on A and you combine them with either adding them together or multiplying them, the result is also a continuous function on A. That's directly what, among other things, theorem 5.4 says. Okay, so that's what I mean by a binary operation. And that binary operation, because these functions are taking outputs in the real numbers, those binary operations have all kinds of properties. And if you've taken the abstract algebra course before, you know what this terminology means. That set actually forms a ring under those two binary operations. It's actually a commutative ring with unity. It's a very nice ring. And in some sense, the algebraic investigation of that ring is kind of an intersection between analysis and abstract algebra, ring theory. Right? If you're currently in the abstract algebra course, I'm making this video on the 14th of March, 2021. I don't know what's going on in the abstract algebra class at this very moment in time, but it's not unlikely that you haven't yet begun your study of rings. You've spoken about these things called groups. So if you forget about multiplication for a second, the continuous functions, they form an abelian group, a commutative group under just the addition operation. The multiplication operation, you can also kind of make a group, but it's a little bit trickier because not all functions are going to have multiplicative inverses. So the whole set doesn't form a group under multiplication, but it does under addition. You add two continuous functions together, you get a continuous function. If you know what I'm talking about, all the group axioms will be satisfied. So there's a little sort of bridge between our course and the Math 343 subject matter. All right. Some of you guys I know, because I did it with you, took linear algebra last fall. Some of you might take it this fall. You've all had or are in the lower division linear algebra course where things are not looked at so abstractly here. But this set, the continuous functions on A, they're a vector space under addition of functions and the scalar multiplication. Multiplying a continuous function by a real number, theorem 5.4 says gives you a continuous function. That'll satisfy all the vector space axioms. In fact, it's a subspace of the set of all functions, the vector space of all functions. Right? So it's a very important subspace. So the continuous functions on a set is a vector subspace of the set of all real valued functions on that set. And again, the kind of intersection between that linear algebra theory that you use and this analysis here is kind of a fun thing to do. It's a bridge between the two subjects. Okay, so hopefully that was interesting to you and kind of motivates you to keep studying or hang in there in your other courses. I'm going to continue on here, repeating really a couple of corollaries. We've already sort of mentioned these things in this course, but I'm going to repeat them because they're important. The first one, and now we can refer to it by number later on in homework or whatever, 5.41, is that polynomials are continuous. So polynomials are functions whose domain is the entire real line. They're continuous at every point in the real line. It's an extremely useful piece of information. Okay. So what's the proof? Well, if you want me to kind of build it from scratch using Theorem 5.40, if you take two specific functions, say f of x is just the constant function 1, okay, I'm going to leave the details to you, but any constant function, and in particular this constant function, is continuous on all of R. Okay, so it's continuous at every x. G, I'm going to define to be g of x is x. The identity function is another name for it. It's also continuous at every x. I'll leave the details to you, but they're not difficult. I would suggest sequential arguments if you want to make life super quick. Okay, well then any polynomial function, I've written one down here. A polynomial function is built out of f and g by taking products. For example, if you want to build x to the n, just take g times itself n times. So any power of x is a product of a bunch of g's. If you want to build one of these terms, or sorry, if you want the constant function a sub n, just take a sub n times f. Okay, and then you can build any one of these terms by taking products of those things. You can build the whole polynomial by taking sums of those terms. Okay, so if you take any polynomial, which just is an expression that looks like that, the AIs are just real numbers, and the exponent is a natural number or perhaps 0. You know, the constant term down here is sort of times x to the 0. So we'll just union 0 on there. And you form polynomials by doing those algebraic operations to the continuous functions f and g. So they're all continuous by Theorem 5.40. Nice. All right. So you don't have to go back and give sequence arguments or epsilon delta arguments. We're sort of using our tools. We're using our tools to build these things. Nice. Along the same lines, I'll leave the details to you, but every rational function, what's a rational function? A rational function is just a ratio of polynomials. So they're going to be continuous, but because we have a denominator here, we have the caveat, they're continuous where the denominator is not 0. So the author is using, it's a common term where the denominator does not vanish, i.e. Does not equal 0. So the denominator vanishing is just another sort of a fancy way to say that it's equal to 0. Okay, so rational functions are continuous. Boom, huge families of examples that we know are continuous without going through sequential arguments every time or epsilon delta arguments every time. So this theory, Theorem 5.40, very important piece of machinery. Okay, the next thing I want to talk about is compositions. Functions, unlike numbers, in addition to being able to be added, subtracted, multiplied, divided, you can also compose them, right? You can plug one function into another. Well, you can't compose any old two functions. You can compose two functions provided the image of one of them is a subset of the domain of the other. So I've drawn a little picture of what I mean by that. I've got a function kind of schematically denoted here by f and a function schematically denoted by g. And I'm kind of indicating here that the image of f of a, those elements in the real numbers that look like f of something from the set A, all belong to B, all right? So in other words, the image of f is a subset of the domain of g being the function b. All right, so when that happens, that means you can take g of f of anything. That is, you can compose f and g. All right, so we've already proven this theorem actually, but it says if you take two such functions, f on a, g on b, and we suppose that f of a is contained in b, like in my picture up there. And if you take some point in a at which f is continuous, and we suppose that g is continuous at the point f of x naught, let's call it y naught. So if you want me to add to my picture here, if I pick some point in a called x naught, and I'm assuming f is continuous there, under the hypothesis, I know that this point y naught, let me just write it down here. Y naught is f of x naught, belongs to f of a, and g is continuous there. I'm assuming that. Then the composition g composed with f is going to be continuous at x naught. And we actually proved this earlier. If you want to stop the video and kind of look back through your notes, we proved it as Theorem 5.25. we didn't have this terminology continuity there. It was just stated in terms of kind of limit properties. But if you go back and look at the statement of theorem 5.25, all we're saying is that, yeah, this second function g is continuous at f of x naught. Cool. So short story, compositions of continuous functions are continuous, legal fine print, provided that, everything is defined, provided that you can actually compose the functions and so on. Nice. That theorem 5.43 was stated at a point if it's true for all points. So if you have two functions f and g, the image of f is contained in the domain of g, and it's continuous at every point in a, and g is continuous at every point on b, then their composition is continuous. Okay, so the composition of continuous functions is continuous. It gives another binary operation, again, provided that you can compose functions on that set C of a above. Okay. So I'm going to end here. This video won't be too long. In this course, we're trying to kind of be rigorous and develop everything either from axioms or theorems. And so we haven't talked about definitions or any properties of lots of functions that you see in calculus. Here, I'm just writing their outputs, so I don't have to keep giving each function a name and so on. But, functions with outputs like e to the x, exponential functions. Its inverse, the natural log of x. The trig function, sine of x, cos x, tangent of x, and so on. Right? Lots of functions that you're familiar with from calculus or maybe differential equations. All of those functions are continuous on their domains. Right? I'm not giving proofs of that. Well, because I'd need some definition of e to the x, right? We defined the number e, and we could talk about exponential functions. It's not out of our range, but we haven't done it yet. But I just want to kind of point out here that we're going to include some of these things in our examples just to keep it interesting, right? Polynomials and rational functions themselves are going to get a little tired here for us if that's all we talk about. So I might include some of these things in our examples. So just to give a kind of concrete example of what I'm talking about, suppose I took some polynomial function like x cubed plus 3. Okay, so we have we know that's a continuous function by the corollary, 5.41, I think it was called. And then suppose I let g be, say, something like e to the x. And by my unproven claim, g is continuous. And the output of x cubed plus 3 is a real number, and the domain of e to the x is all real numbers. So the image of f is contained in the domain of g. Okay, and things are continuous on both sets. So if I compose them, it would be a function whose formula looks like that, e to the x cubed plus 3. Okay, that's continuous on the real numbers by the theorem. It's a composition of two continuous functions. So would say like sine of x cubed plus 3 and so on. So you can often break a function down either using addition, multiplication, so on, like we did for polynomials and rational functions, or even break one down using composition, right? This function whose output is e to the x cubed plus 3 is a composition of two functions. If you sort of follow what happens to an input, that input is first sent to x cubed plus 3, and then that is taken and made the exponent on e. So that two-step process is a composition, and both steps are continuous, so the composition is continuous. Okay, so that's where we're going to end this video now. Thanks for listening.